It's this. And this is what type of function? It's polynomial. It's quadratic, right? But notice I have not told you what A, B, and C are. Oh, you know what? I made a quick little error there. Hold on. Replace that C with 3. Pardon me. Make that a 3, not a C. But this is still a quadratic, right? But I'm not telling you what A and B are, which means this could be a lot of different quadratics, right? It could be like 4x squared plus 9x. It could be negative 2x squared plus 5x plus 3, right? So I'm not telling you what A and B are. But we all agree it's a parabola. And then look at this last one. This last piece, which would be over here, is what type of graph? It's a polynomial, but even more, it's linear, right? 2x, and then these, if we assume that A and B are numbers here, if I give you some numbers, you add them up or subtract or whatever you do here, then it'll be like maybe 2x plus 10, right? And that's a line. So we have a rational function, a parabola, and a line. Understand? And when I graph them, what they look like together all depends on what? What are the two things that will dictate what this thing looks like? This one just looks like whatever it is, right? It's a rational function. I can't change it. It is what it is, isn't it? But this one, can I change what it looks like? Yes, by changing A and B, right? So if I use a negative A here, it's going to open down. If I use a positive A, it's going to open up, right? And then here, this line is also dictated by the A and the B. So I know I have three pieces, rational, parabola, line. But what they look like exactly is actually dictated by the values of A and B. Okay? So let me show you, I've put together a little picture here for you of what we've got going on. I have a rational function, and you can't tell this is the rational function, but here it is. And then it switches over to this parabola. It looks like a line, but it's a parabola. And then it switches over to this straight line. And I've made this program where I can change the values of A and B. So watch what happens if I change the values of A and B. Notice that changing A has an impact on both the blue and this is supposed to be gray, but it looks black, right? So the blue and the black one, if I change A, changes those two, doesn't it? That's because I'm changing this number and this number. And if I make A negative, what's going to happen? It's going to flip that parabola over. Do you see that happening? Okay, and if I change B, it's also going to have an impact on things. Because B is the number here and the number here. So what do you think I'm going to ask you? Not the limit. Not the bounds. What is this section about? Continuity. Is that picture continuous? Is this a continuous function? No. I sure would like it to be continuous, though. Do you think that you can find the A and the B that would move everything together perfectly? Like, if I move this A around just right, maybe I can get them to line up, like you see. But if I move B, if I change B, it screws up A, so I have to go back here and shit. You know, and I try to get them, I'm trying to get this thing to be continuous, to paste together perfectly. That's what I'm going for here. And that's the question. So let me post the question up here and then we'll go do it. Find A and B such that what? F is continuous everywhere. I haven't been using the sticks today because there's really not a whole lot of things I can be asking you right now. Find A and B such that F is continuous everywhere. That is the question. All right, well, let's go back and take a look at the picture again. I'm going to switch up A and B here. Bring A up there. There we go. Okay. Jace isn't here. Derek, you were called on last class, weren't you? Franklin, you weren't called on last class or the class before. All right, so you're up. I just have a quick question for you. Is this function continuous to the left of this point here? Out here, is that function continuous? Out that way?
Or are you including like right at?
No, oh, no, just to the left over here, is it continuous? Yeah. Okay, you're looking at this, right? But actually, I want you to look up there. Which function is it that I'm talking about? Top, middle, or bottom? Which function is the one over here? It's the top, because we're the top function whenever x is less than 2, right? Now, it may be hard to see this, but this is 2 right here, okay? And then this is 3, just so you all know, okay? So to the left of 2, I'm this function. And this is a rational function, right? And rational functions are continuous on their implied domains. And there's only one number that causes a problem here, and that's what? 2. But we are looking to the left of 2. So to the left of 2, I've got a continuous function, don't I? Okay. Marissa? How about between 2 and 3? This blue function. Between 2 and 3, is it continuous? Yes? Why? Look at this right here. Why can you tell me that that's continuous? Okay, there's no holes. What type of function is this? Quadratic. And quadratics are polynomials. And polynomials are continuous everywhere. All right? So I know that, again, recapping, Frank said that to the left of 2, we're continuous. Marissa's saying that between 2 and 3, we're continuous. And Luis, to the right of 3, over here, we are continuous or not? So, okay, so why? Which one are we looking at there? The linear, right? And a linear function is continuous everywhere because it's a polynomial. So we have continuity to the left, we have continuity in the middle, we have continuity on the right side. The only places we don't have continuity is where? At where? Savannah? Exactly, at x equals 2 and at x equals 3. That's the only places that we don't have continuity, right? That's where we need continuity, right? That's where we need it, yes.
So you're saying that the middle one has continuity?
It has continuity just in here, just in this little blue part. We know at the ends it's all jacked up.
Yeah.
But in the middle, I could draw without picking up my pencil. And I know that because it's a parabola. Over here, this is all nice because it's a line. Over here, this is a rational function. It's nice too.
So we're not looking at the whole here?
We are going to look at the holes, yes. But I want to clarify the reason that we are not looking anywhere else but at 2 and 3 is because everywhere else we're fine. Okay? So to kind of recap what we just stated is this. We need f to be continuous at x equals where? And 3. If we can figure out what makes x continuous at 2 and what makes f continuous at 3, then we will have a continuous function everywhere, right? Okay. Michael Sanchez. Did I call on you last time? Did I call on you last time? Did I call on you last time? No. No? I don't think I did. Michael, do you remember what the definition is for the limit, for continuity at 2? So I'm putting you on the spot here. When we say we want f continuous, I'm going to put cont dot, all right, instead of writing continuous, at 2, what is it that must be true? This is what we started class with.
There's no holes or breaks.
Okay, no holes or breaks, but algebraically, what was it that something had to be equal to something? Do you remember that?
Function A had to be equal to function B.
The function at A had to be equal to, not B, but the limit. The limit. Look, I'm going to go back. I'm going to roll it all the way back up to the beginning of the section. There it is. That right there. A function f is said to be continuous at x equals a if the limit as you approach a of the function equals f of a, right? That was the definition we started class with. And we did a couple of visual examples, right? So we just said, in order to make this function continuous everywhere, we only need to make it continuous at 2 points. Everything else is fine. So first, we want continuity at x equals 2, which means we need the limit as x approaches 2 of the function to be equal to f of 2. Do you all agree that that is the definition? We need that to be true. This must be true for us to be able to say it's continuous at 2. Now, Chris, I call on you last time? I didn't, did I? Thank you all for your honesty. Chris, what's f of 2? I need to figure out what this is and what this is. I'm going to start off with this. What's f of 2? So come over here, plug in 2. So if you plug in 2 to this, which piece of the function are you using? Chris, are you using this? The middle one, right? Because if we're plugging 2 in, x is going to be greater than or equal to 2, so we're using this function. Does everyone agree? And we're going to plug 2 in for what? For x. Plug 2 in for x here, Chris, and tell me what you get.
So
2 here, right?
Yeah.
So 4a. So do you all agree that the right side of this is 4a? Then, Chris, keep going, plus? You're plugging in 2, right? 2 times b, b times 2, same thing. And then plus 3, right? Do we all see that? F of 2 is this. Now, I don't know what a and b are. That's what I need to figure out. But I know this much so far, right? Now, good, Chris. Sophia, did I call on you last time? Sophia, you get the limit. I need this side. I need you to approach 2 and tell me what's happening to the function. This is probably going to be the hardest part of the problem. So when I'm approaching 2, Sophia, I'm going to help you through this. When I'm approaching 2, that means I'm not 2, right? I'm getting close to 2. So are you even close to 2 down here, Sophia? No, you only use this if you're close to 3, right? Now here you're close to 2, aren't you? But we've already used this, haven't we? We used it for the other side of the equation. This one up here is close to 2. So why don't we take the limit of that piece? Does that make sense to you, Sophia? I'm going to use that for the left side. So the left side is going to be the limit as x approaches 2. And I'm going to put the function there, x squared minus 4 over x minus 2. Does that make sense? Now, Sophia, when you take this limit, what do you get? Like, what form are you getting when you take that limit? What do you get on top and what do you get on bottom when you just try and directly place 2 in there? 0 on top and 0 on the bottom. 0 over 0 is bad, right? And what do we do when we see 0 over 0? Some sort of algebra, right? So we actually have to do this limit now. So we're going to do a factoring on the top, difference of squares. Limit x approaches 2, factor the top, x plus 2 times x minus 2 over x minus 2 equals 4a plus 2b plus 3. And these cancel, right? X minus 2's cancel. And now Sophia, you just want to finish it off? What's that left side, the limit, going to be after we do that canceling? 4, right? Everyone? 4? Okay, so here's what we have. Here's what we have so far. We have that 4, that's the left side, must be equal to 4a plus 2b plus 3. We all on board with that?
Yes.
We're trying to find a and b, aren't we? The problem is we only have one equation and we have 2 unknowns. You cannot solve for a or b if you only have one equation and 2 unknowns. What I need is another equation. I need a second equation with a and b in it. And then I would have 2 equations with 2 unknowns, right? Where in the hell are we going to get another equation from? The fact that we also need this to be continuous at 3, right? We've only used that we needed it to be continuous at 2 and got this. Now let's go see what it takes to make it continuous at 3. And when we do that, we should get another equation. Okay, so now restarting, we want f to be continuous at 3. All right. Let's see. Nas, it's your time to shine. Nas, if I want to be continuous at 3, where the heck did you go? There you are. If I want to be continuous at 3, then that means I need what to be true? So what's the definition of continuous at 3?
Whatever to the right
Okay.
equals f of 3.
Okay, so equals f of 3,
The limits from the right.
the limit as x approaches 3 of the function. Right, this is what it would mean to be continuous at 3. Now, I think I understand what you're saying, only from one side.
Yeah, because the other side is going to be different.
The other side's going to be different. I'm going to deal with that as we work the sides out.
Yeah, I see.
But this is the definition of continuity at 3. Do we all agree with that? Okay, so now Nas, let's keep going.
Okay.
Nas,
So f of 3,
what's f of 3?
Plug in 3, 2, 6.
So in here, right?
Yes.
And that's because you have that bar under here. So plugging 3 in for x,
Yes.
6.
6 minus a plus b.
Okay, good.
And for the limit, do we go from the left or
Well,
right?
we're going to be coming in, we're going to be trying to approach 3, right?
Yeah, from the
It's going to be from the left, but I think it's easier for students to visualize it this way. You already know what's happening at 3, right?
Yes.
You want to know what's happening near 3.
Yes.
It wouldn't make sense to plug 3 back into this, because if you plug 3 back into that, you're going to have the same expression equal to the same expression. That tells you nothing. So it makes more sense to plug the 3 into the one that you haven't used, which is the one in the middle, which would be a left-hand limit, but we're going to go here. And why aren't we even messing with this one now? Because that's over near 2, right? This one's close to 2 and 3. In this case, we're going to be approaching 3. So I'm going to be doing limit x approaches 3 of that middle function, ax squared plus bx plus 3. Make sense or not? Question?
So even though it tells like x less than 3, but still we're gonna.
Yeah, even though it says less than 3, remember, in the limit, I'm getting close to 3. I'm never 3, right? So being a little bit less than 3 is still okay. It's like, remember when we did the number line and we were saying here's 3? We're actually coming in like this. That's close to 3, right? But less than 3? So that's okay to use this, right? X is a little bit smaller than 3. I think, Nas, that's what you were saying. It's like a left-hand limit is what we're doing. Okay, now, what does that go to? Plug in 3 for x. So 9a, right? 9a
plus b
plus 3b plus 3, 6a, minus a plus b. And voila, look at that. We have a second equation that has a and b in it. So we have 2 equations and 2 unknowns, don't we? Yeah, you have options at this point. We're going to work it all the way out, but we have options. All right, so we're getting there. We're not there yet, but we're getting there. So now let me clean my first equation up a little bit. Do you all agree that this is 4a plus 2b equals -1? So all I did was left a and b on one side, took my, not negative 1, sorry, positive 1, and then took the 3 and subtracted on both sides. So I get a nice clean equation. Can I do the same thing here? Get all my a's on one side, all my b's on the same side. So how about add a? So 10 a's. I'm going to put that equation underneath this one. 10a. How many b's do I have? 2 b's. And that should be equal to, so I just bring that 3 over, subtract it, right? And we just get 3. Okay? And this, you'll recognize from college algebra, is a system of equations. And we need to solve it. And when it comes to solving systems of equations, if you don't know what I'm talking about right now, then I would just jot down Google system of equations, YouTube system of equations, right? So this right here, we have 2 options to solve. We have elimination and we have substitution. Those are the 2 methods. Elimination, right now, when I'm looking at this, elimination to me is the way to go. And the way elimination works is you look at the A's, you look at the B's, and you see if there's any way that you could just get these to cancel easily. And you can see that since these are both 2B's, if I make one of these negative 2B and add down, the B's will cancel. So what I do is I multiply either the top or bottom row by negative 1, and I distribute that through the entire equation and create a new equation. So this becomes, what's my top equation now? Negative 4a minus 2b equals negative 1. And then I just rewrite the second equation. And this method I'm using, I said you could use 2 methods, elimination or substitution. The method I'm using right now is the elimination, because it's easier, I think, on this problem to do it. And now once you're there, what do? Just add straight down. Okay, so just add straight down. This and this add up to be 6a. Negative 2b and 2b cancel, and then equals over here we get 2. And voila, I have a single equation with a in it. And so I can solve for a. So a must be 1/3. Once I know what a is, I can always go back and get b. And the way I do that is I take this answer and I plug it in where? Actually, any of them. You can plug this a into this one, or either one of those, doesn't matter. If you plug a in 1/3, then you're going to be able to get your b. So I'll do that. How about I plug that into, I'm just going to grab this one. Grab that one right there. Let's plug in 1/3. So 4 times 1/3 plus 2b equals 1. And now you solve for b. So 4/3 plus 2b equals 1. Subtract 4/3 from both sides. So when I subtract 4/3 here and subtract 4/3 here, 1 minus 4/3 is negative 1/3. I'm trusting you can do that. And then I'm dividing by 2, so I get negative 1/6. All right, so that only took us, what, like half an hour? So f of x equals x squared minus 4 over x minus 2 if x is less than 2. And then now I know what a is, don't I? A should be 1/3. 1/3 x squared plus b, but I know b needs to be minus 1/6. X plus 3, as long as x is between, as long as x is between 2 and 3, like that. And then 2x. Then I'm supposed to take negative a and add b. What's negative a, add b? Negative a is negative 1/3, right? Negative a is negative 1/3. And so if I take negative a and add b, I'm doing negative 1/3, and I'm adding this, which means minus this. And so put that together, you get what? Negative 3 over 6, which is? Negative 1/2. if x is greater than or equal to 3. There we go. If I graph that on my computer now, I should have a function that is continuous everywhere. It's going to be a rational function for a while. It's going to switch over very smoothly to a parabola and then transition very smoothly into a line. And I can verify it on my computer by coming down here and changing my value of a here on my computer to 1/3. That didn't work. Changing my value of a to 1/3. That didn't quite do it yet, right? But now I'm going to change my value of b to -1/6. And if I did it right, or if we did it right, they're all going to line up. Right there. See that? Okay. Students don't like that section. Let's see where we are here. Today is the 7th, and we were supposed to finish, well, we should be done through all of chapter 1 today, which we are. Yes?
So you said this one, this problem is going to be basically, is going to be based on a quiz, not a test. So how long would it be expected for us to take just like on this one problem?
If you do your homework for this, you'll see that I believe the problems in the book, let me just double check this, 1.5. Man, this is actually a homework problem. This is a homework problem. But number 33, number 33, this was number 34. Number 33 in your homework is similar to this, but it only has 2 equations and 1 unknown. And so you never have to set up a system of equations. All right? So it's much shorter because you only have, if there's only 2 equations, you only have one place where you have to make it continuous. And so you only have to set up that limit one time and then do left and right equal, and you'll be able to solve for the a or the b, whatever it is, you'll be able to solve for it right away. Does that make sense? So it takes a lot less time. I put up here kind of the end all be all, like this is the worst it gets type thing, but I think you'll be happy when you see number 33. And that's what I would expect on a test, something like 33, okay? But this is an excellent problem because it shows you, how you can use a system of equations to solve something like this. It just kind of pops up out of nowhere. All right. I don't think we have enough time to start chapter 2, but just looking at our schedule, our first test is scheduled for Tuesday the 19th. So that means we have next week, okay? Oh, yeah. We have next week, we have 2 lectures. We have a lecture on Tuesday covering 2.1, which is derivatives and rates of change. Then we have another section on Thursday, 2.2, the derivative of a function. And then the following Tuesday, we have our first exam. And that first exam will cover at least through 2.1. So what we do next Tuesday will be on the exam. What we do next Thursday will not be on the exam. All right, so you have a little bit of a buffer there, not much, but in theory, you have a whole week between the last piece of information on the exam and the exam. Let's sign in. Let's start back here. Another question, yes? What was your questions? Is 1.1 and 1.2 going to be on the exam? Probably not. Your exam is mostly going to be limits. I mean, from 1-3 on, right? Yeah, the new stuff really starts in 1.3, and that's what the test is going to emphasize. Yes?
Pretty sure I asked you this already, but there's no review. We're not getting a review, right, for the test?
I think what I'm going to do is I'm probably going to get up here and be looking at one of my old tests, or if I have the test done by that time, I'm going to look at the test, and I'm going to sit here and just kind of talk through, like, you know, here are the things you should focus on. But I'm not going to hand out a review per se and be like, go do these sample problems and you'll be fine for the test. Because I want you to get better at studying for tests, at preparing for them. Pardon? Whatever I say about the, yeah, that'll be on video. Mm-hmm. Any other questions? How are y'all feeling about this? I mean, 1.6, I know you just saw it, but overall, does the test seem frightening? Or y'all?
I think the quizzes are more sensitive.
Quizzes are a little more frightening?
I've
Yeah.
never had testings already until like that day.
Well,
I guess there's just a lot going on. Like
Yeah.
each desk, and then people were still coming in, and then there was like only 15 minutes. And I'm like, whoa.
yeah.
A lot.
I know anxiety is a real thing, you know.
I had the quiz, like, I was like,
You can go after you've signed in.
in my
I
head.
have nothing else. What's that?